Hello friends, in this video I'd like to solve the following problem from the Romanian International Mathematical Olympiad Team Selection Test 1987, problem number 7. We wish to find all positive integers n such that 3 to the power of n minus 2 to the power of n is divisible by n. It's a nice problem from number theory. Here are my hints. The heart of this reasoning is the following well-known theorem, which says that if a, b, k, and l are positive integers, and if a and b are co-prime, a is less than b, and k and l are distinct integers, then GCD of b to the power of k minus a to the power of k and b to the power of l minus a to the power of l equals, in fact, b to the power GCD of kl minus a to the power GCD of kl. It's a well-known fact from number theory. I will not prove it here because it's well known, as I said, and I wish to keep this video relatively short, but I may prove it in the near future. For example, it is stated in Concrete Mathematics textbook as one of the exercises of 4th chapter. Well, the general idea of this proof, of this theorem, is to use Euclid's extended or just Euclid's algorithm to find some recursion and to build the result from there. Let's assume that we know this theorem to be true. In particular, this theorem has one particular important consequence, that if we have some positive integer m, or non-zero integer for that matter, and if m divides b to the power of k minus a to the power of k, and at the same time n divides b to the power of l minus a to the power of l, well, then it divides GCD of these two numbers, and so, because of our equality, m also divides b to the power GCD of k and l minus a to the power GCD of k and l. So this is a general theorem which we'll use. And the rest of my hints: first, check separately n equals 1, what happens then? Then think about, can 2 divide n? Can 3 divide n? Probably not. And finally, suppose that we have some number n greater than or equal 5, because 2, 3, and 4 won't do. And suppose that our divisibility holds. Consider p to be the smallest prime divisor of n, and use Fermat's little theorem to prove that p divides, here's a typo, p divides 3 to the power of n minus 2 to the power of n. And moreover, use the theorem which I stated to get some kind of, sorry, there was, sorry, once again I made a typo, 3 to the power p minus 1 minus 2 to the power p minus 1. P divides this number. And use the theorem which I stated and Fermat's little theorem to get some kind of contradiction. So give this problem a try, and I will see you in just a minute. Okay, so you know what, let's keep our theorem written, stated. Now, first case, if n equals 1, then obviously n does divide 3 to the power of n minus 2 to the power of n. Nothing interesting. Well, notice now that if 2 divides n or 3 divides n, then what exactly? Notice that then 2 cannot divide 3 to the power of n minus 2 to the power of n, or it's in the first case, or and maybe. No, let's keep it. If 2 divides n, then 2 does not divide 3 to the power of n minus 2 to the power of n. So n cannot also divide this number. Okay, if 3 divides n, then 3 does not divide 3 to the power of n minus 2 to the power of n, because 2 to the power of n is not divisible by 3. So n cannot divide 3 to the power of n minus 2 to the power of n. Now, suppose that n is greater than or equal 5, 2 does not divide n, 3 does not divide n, and that our divisibility somehow holds. So n divides 3 to the power of n minus 2 to the power of n. Crucially, consider now, let p be the smallest prime divisor of n. Now notice the following. Then of course we have, if n divides 3 to the power of n minus 2 to the power of n, and if p divides n, well, obviously p divides 3 to the power of n minus 2 to the power of n. Okay, so let's mark it asterisk. But also by Fermat's little theorem, write it in pink, by Fermat's little theorem, well, p divides 3 to the power of p minus 1 minus 1, and p divides 2 to the power p minus 1 minus 1, because p is not divisible either by 2 or 3. So if we subtract these two numbers, we get that p also divides 3 to the power of p minus 1 minus 2 to the power of p minus 1. Let's mark it double asterisk. And now it's time to use our powerful theorem, or rather the corollary of our theorem. We have established that p divides some difference, p divides some other difference, so it must divide difference with GCD in the exponents. So by our theorem, p must divide 3 to the power GCD of n and p minus 1 minus 2 to the power GCD of p minus 1 and n, by our theorem and by conditions asterisk and double asterisk. Okay, but now comes the interesting part. Because p is the smallest prime divisor of n, it was the smallest prime divisor, so what is this GCD? It must be 1. There cannot be any prime which divides both n and p minus 1. So notice that there is no prime, q such that q divides p minus 1 and n, because if it divides p minus 1, it's less than 1, and if it is less than 1, it doesn't divide n, because p is the smallest prime divisor. So GCD of p minus 1 and n, crucially, this GCD equals 1. They are coprime. That means that p in fact must divide 3 to the power of 1 minus 2 to the power of 1, which is 1, of course, and we get a contradiction because no prime can divide number 1. Contradiction. So in other words, there is no such number n greater than 1 which satisfies our equation. So all in all, so maybe let's write it, that n divides 3 to the power of n minus 2 to the power of n if and only if n equals 1. It's the only possibility. In positive integers, of course. And that's it. That closes our problem. Very nice problem, and I suggest that you become familiar with this theorem. It happens to be very, very useful that GCD can change its place from GCD can be put in the exponent, provided that these assumptions are met. As I said, in the future I may prove it directly by Euclid's algorithm. Yes, that's it. The only solution is n equals 1. Thank you very much for watching, and I will see you next time. Goodbye.